This is a video introduction to mass spectrometry. This video covers material from Chapter 21 of your analytical chemistry textbook. A mass spectrometer is a detector essentially for ions. And so the first thing we have to do to our sample if we want to analyze it in a mass spectrometer is we have to ionize it. So in general, a mass spectrometer, the first thing a sample sees after the injection port is an ion source that turns it into ions. Those ions are then separated by their mass using some sort of separation region and then sent to an ion detector of some kind. And then we have a computer for data analysis. Now, since these ions are being separated by their mass, this is pretty sensitive to contamination because we want the ions to come from our sample and not from anything in the atmosphere. So this whole region here, the ion source, the mass separation region, and the ion detector, is under high vacuum. And the kind of mass separation and the kind of ion detector dictate how high that vacuum has to be. In some cases it can be reasonably low. In other cases you have to have an extremely low volume in order to get a good mass spec operation. The mass separation region separates ions based on their mass to charge ratio. And so the mass to charge ratio is exactly what it sounds like. It's the mass of the ion divided by the charge on that ion. Ideally, when ions are produced in a mass spectrometer, they have a charge of either +1 or -1. And so the math here is easy. Whether the charge is positive or negative, it's conventional to express the mass to charge ratio as a positive number. So we can do an example of finding the mass to charge ratio for a methane ion, CH4 plus. Most mass spectrometer techniques are sensitive enough that it matters whether this is carbon-12 or carbon-13 or carbon-14, and also whether it's hydrogen or deuterium. In this case, we use carbon-12 and regular hydrogen. So the mass is the mass of a carbon-12 atom plus the mass of 4 hydrogen atoms divided by the charge plus 1, and so in this case we get 16.035. Depending on the kind of instrument you're using, you may have that number of significant figures, you may have more, or you may have less if it's a less sensitive instrument. The mass analyzer is going to largely dictate how sensitive your instrument's going to be, and the simplest one of these is a quadrupole mass spectrometer. It's called a quadrupole because it has 4 charged poles that actually do the mass separation. So the 2 of the rods are positively charged and 2 are negatively charged, and the magnitude of that charge fluctuates. The degree of fluctuation dictates what size ions make it through and hit the detector. If the ions are too light, they'll be deflected too much and hit the poles. If they're too heavy, they'll be deflected not enough and they will miss the detector. They'll take on a path that doesn't hit the detector. The detector then, the detector detects everything that hits it. And the way that the mass separation is done is by changing the magnitude of the voltage on those quadrupole rods, and so that at first light ions make it to the detector, and then later in the scan heavier ions make it to the detector. Sort of the very simplest ion source that you can use is electron impact ionization. And so this happens before the mass analyzer region. In an electron impact ionizer, your sample is injected into the instrument, starts at room pressure, and you inject it into the first pumping stage, which is sort of at a millionth or at a thousandth of an atmosphere or so. And it then goes through a very small pinhole that's at a millionth of an atmosphere, and in that region there's an electron source, just a hot filament. The hot filament produces energetic electrons. When they hit your sample, the electron knocks off an additional electron and leaves you with a positively charged ion, which is then drawn into a very low or much lower pressure region, a billionth of an atmosphere, in which the mass analyzer exists. The problem with this sort of ionization method is that it causes a lot of fragmentation. So these high energetic electrons, in addition to knocking off an electron, they can also knock off pieces of your molecule. So the mass spectrum that you see here is the mass spectrum of formic acid. On the y-axis of this is relative intensity. This is a measure of how many ions of a given mass hit the detector. and on the x-axis is the mass to charge ratio. So you see that in this mass spectrum, the main peak is not the mass of a formic acid ion, just the formic acid molecule minus 1 electron. You do see that peak, but a much bigger peak is at mass to charge ratio 29, which is a formic acid minus 17. So fragmentation has happened. And the fragmentation that's happened is the OH group on the right side of the molecule being knocked off, leaving a CHO plus ion that has a mass to charge ratio of 29. All right. In general, there are some common mass losses that you see in electron impact mass spectrometry. A loss of 15 corresponds to a CH3 group being knocked off, 17 OH or NH3, 29 C2H5, so 2 carbon being knocked off of a hydrocarbon chain, and so on. So for formic acid, we start out with something that's 46 AMU. The M plus peak is this thing with an electron knocked off. So we call this the M plus peak, the parent mass peak, and it has a mass to charge ratio of 46. If the formic acid molecule loses 1 hydrogen, which can happen, we get the peak at 45. Loses 2 hydrogens, we get the one at 44. And the biggest peak, 29, again, comes from the OH group being knocked off. So electron impact ionization is used because it's cheap and relatively durable, and it will ionize everything. You get a high ion current, it's easy to detect, that sort of thing. Fragmentation can be useful because you can get structural information from it. If the molecule always loses chunks of 15, you can infer that there are many methyl groups on it. Fragmentation is a bad thing, though, because it makes it hard to determine the parent ion peak, the actual mass of the analyte. A bad thing about electron impact ionization is that the molecule size is limited. Very big molecules are just not going to be ionized efficiently by this technique. And also the samples have to be in the gas phase because of the pressures that are involved at the ionization step. So a question you could ask, and I'll ask you this in lecture, is can we use electron impact mass spectrometry as a detector for HPLC, or do we need to use a different kind of mass spec? So a different kind of ionization is chemical ionization, and in contrast to electron impact, this is a gentle ionization method. The general trend here is that whatever ionizing agent you use, it's going to transfer a proton to your sample, your analyte, and then your analyte will be an ion and it can be detected. This is a much gentler process than using energetic electrons to knock off additional electrons, and so you get much less fragmentation. In either case, if we use mass spectrometry as a detector for chromatography, which we commonly do, we get a chromatogram in the same way we got for HPLC or GC. So in this case, we have a detector signal, total signal versus time. The way that we get the signal at any given point, at any 1 second or half a second or however good your detector is, the magnitude of the detector signal is the sum of all the peaks in the mass spectrum. So the instrument collects a mass spectrum, adds up all the heights, and plots that as 1 point on the chromatogram. Later time does it again. So when you use chromatography mass spec, you get 2 kinds of information from your chromatogram. You see there is a peak at time 125 seconds. And if you look at the mass spectrum of the peaks that produced that point in the chromatogram, you can get chemical information about what the analyte was that came out at 125 seconds.